So hi everyone, today we start the final block of topics for this course, which will be relevant for the exam, but not for the midterm that you'll have on Saturday. So, and I reshuffled topics a bit, so it won't be exactly as promised in the schedule, but the topics will likely stay the same. So the first one will be the social learning. So today's lecture is not kind of, one model, it's more like an overview of this field. So the first thing that I want to discuss is like what is specific about this type of learning. Because for instance, when we started experimentation, it was also some kind of learning, right? Because you had some experimenter who had several options. In Bernoulli bandits, this was drugs. In exponential bandits, these were just arms of some bandit. But in any case, in these frameworks, there was some unknown fundamental, which the experimenter gradually learned. So what is specific about this type of learning, about social learning? Like the standard setup is as follows. So there is still some unknown fundamental of the world, which is payoff relevance, right? That is, the more accurate is your knowledge about these fundamentals, the better decisions you can make, right? But what is specific about how this learning occurs is that it occurs in stages. That is, you do not have an individual experimenter here anymore. So you have some experimenter who tries some options in say current period, then reveals some information somehow. I mean, like it's vague. So I do not specify how this information or something is revealed. And then he just goes from the market, and then the next experimenter enters and observes some results of the previous individual, right? And then based on the information this individual possesses, he or she makes optimal decision. And again, with these actions, some information is revealed for further generations, and then again and again. So you don't have an individual experimenter anymore who remembers everything what happened in previous periods, but you have like a queue of individuals who try some options. And standard questions in these type of models is the following. Like, will collectively individuals learn this fundamental or not, right? So it's like, will collectively they know the value of this fundamental in say very long time horizon, or they are kind of doomed to have only kind of bounded views about this fundamental, or maybe it's even worse, that they can believe in long horizon in something wrong, right? So that's exactly what we're going to try to analyze today. And so examples of such learning schemes is the following. So our first is, for instance, like, restaurants, hotels, and something like that, because, for instance, take a hotel, you want to go somewhere, you Google these particular hotels that you want to stay, and what you observe frequently is just reviews from previous customers, right? And this is exactly information accumulated for you by the previous experimenters, right? And then based on this information, you decide whether you want to go to this hotel or not. And if you go there, right, you get your experience and then potentially write a review for further generations as well, right? And then the next one who wants to go the same place as you did, he or she also observes your review, and this goes on and on. And the question is like, will it converge? Will basically the rating of the hotel in Google converge to its actual, value. The same with restaurants, also with new products, like, when they just launched, no one knows their exact quality, like the exact value for a customer. And then, just people buy it gradually, they accumulate experience with it, and they share these experiences, and then next generations can make better decisions whether to purchase these items or not. The same with new technological standards. Again, it's something new that you just try gradually. With these tries, you accumulate information, then decide whether to adapt it or not. So the plan for today is to view two kind of simple models. One will be like a toy model, which will illustrate a phenomenon called herding. And the second model will be just a paper which generalizes this herding idea to like a very general framework. And we'll just, mention the results of this paper without actually solving the model which is given in this paper. So let us start. So first, what we'll study is herding. And herding is exactly like, herd is, as you may know, it's the group of, let's say, sheep, cows, whatever. And herding is actually, it's like collective behavior, which is just, imitates the behavior of others, but like not your views. So why do we observe sometimes things like herding, right? Because sometimes we are influenced by the opinions of others. And the reason for that is quite simple, because if you have lots of people who believe like the thing is in a particular way, then you just see that, they also potentially have some like private views, private information about this phenomenon. And, because there is a large number of them, probably you believe that in aggregate, they know better than you alone, right? And therefore, you just disregard your personal views and rationally herd with the crowd, because, there are just too many of them to be that they are erroneous, right? That they are not correct. And frequently, this behavior is perfectly rational. And the problem in this is that frequently, these kind of large herds, such as the large groups of people who act in the similar way, it can be that they all do wrong things, right? Merely because they all believe in this kind of system, right? Because it's like, if you have a herd of 1,000 individuals, probably each one believes that, 999 people can be wrong, right? And therefore I will just herd with them. And they all believe this way, right? Then it's kind of self-fulfilling expectations, basically, right? They all rely on others, even if what they believe is contradictory to what all others do. And sometimes we can observe such herds, such herding behavior, right? And the goal, our next goal, is just to see how this herding behavior can occur, right? Sometimes this herding behavior is also called informational cascade. I cannot say it's a good term for expecting it, but for labeling it, but maybe based on the next model, it will be, more clear why this term is used. So the model is as follows. So we'll get back to discrete time. So we have discrete time starting from period 1 and infinite horizon, and there is some underlying state of the world, right? So like true value of fundamental, and this fundamental is just some theta. And because we assume that this uncertainty is binary, so the state can be, state is binary, we can assume that these two states are just numbers. That is, say, one state is just 0 and another state is just 1. Numerical values here are relevant. These are just 0 and 1. These are just labels, right? And for simplicity again of the model, let us assume that ex ante, before the game starts, both values of theta are equally likely. That is, it's equally likely that you are in state 0, and like that is, with probability 1/2 you are in state 0, and with probability 1/2 you are in state. And then you have a queue of agents. That is, say, they are already arranged in queue. And in period 1, the first agent will arrive, do something, which we'll illustrate next. Then there will be some results of these actions, and the next second agent will arrive in the second period, again, do the same things. And so you have one agent per period arriving to the market. And next, we just illustrate what time t agent does. So the goal of any agent in this model is to match the state with action, right? So we assume again that actions of the agents here are just binary. So they can make action 0 or action 1. And their goal is exactly to match the state, right? So it's perfect, it's ideal for them to make action 0 when the state is 0, and it's ideal for them to make action 1 if state is 1. In these cases, they receive payoff of 1, and when they erroneously, like say, choose action 1 in state 0 or choose action 0 in state 1, so they make wrong choice, and in this case, we say that they get payoff of 0. So their goal is exactly to match the state with their action. And like, what do they observe? So suppose you have time t agent, and this time t agent arrives to the market. So what this agent observes, he observes the actions of all previous agents. That is, when the first agent arrives, he doesn't observe anything, right? Because there are no previous agents. But let's say the second agent observes the action of the first agent, right? The third observes the actions of the first and the second agent, and so on, right? So time t agent observes all the actions of previous agents, which are x1, x2, and so on, right? And on top of it, each agent observes private signal, right? Which we denote as ST. And based on this information, right, he decides on his own action, XT. So these actions of previous agents, you do not observe their signals, right? So here, you do not observe, let's say, the second agent who arrives in the second period, he doesn't observe a private signal of the first individual. He observes only the action made by the first individual based on this signal, but not the signal itself, right? Just in action. Therefore, there is some kind of information loss, right? So you do not observe like the arguments because of which one agent made a particular decision. You just observe the decision. And so you observe these actions, and you observe your own signal. And your own signal is somehow suggestive about the true state of the world. So we assume that there is some exogenous value p, which just measures the accuracy of this signal. We assume that you receive signal, let us say, when true state is 0, right? With probability P, you will receive signal that at 0, and with probability 1 minus P, you will receive like a wrong signal as t equal to 1. And vice versa, when true state is 1, with probability P, you will receive signal that it's 1, and with probability 1 minus P, you will receive signal that it's 0. So for instance, when P is equal to 1, right, then the signal is perfectly revealing, right? Because when it's 1, when the state is 0, you certainly receive signal 0, and when state is 1, with certainty again, you receive signals that it's 1. When it's, for instance, 1/2, right, it's perfectly uninformative, because with the same probabilities, which are all the time 1/2, you receive either signal, right? So it's absolutely uninformative, because this, you know, in both cases, right? So, you know, because you receive a particular signal with probability 1/2 in both states, right? And therefore, according to Bayes' rule, you won't change your prior. What we assume is that it's somewhere in between. That is, it is suggestive, but it's not perfectly real. That is, once you receive signal 0, let's say, you certainly understand that it's more likely that the state is theta equal to 0 rather than theta equal to 1. And when you receive signal equal to 1, you understand that it's more likely that the state is 1 rather than 0 in comparison to your prior, right? But anyway, you are not 100% certain of this thing. So all in all, in any moment in time, when you make a binary decision, what you observe is just the decisions of the previous agents in the queue and your own private information, which is suggestive, right? Which has some value for you. And the question of this model is actually to describe what any agent in the queue will do. That's the goal. And actually, this particular problem is quite simple, but it's, you know, there's no elegant solution for it. So what you do here, you just analyze the decision making of first individuals and the second individual and the third individual and so on. And then you see a clear pattern of this behavior, and you just see how it will be in any period afterwards, so that you can write the actual strategy. So we'll just do this. And let us start with the first period. It's particularly simple here. Remember that we assume that initially, before the start of the game, both states, both thetas, 0 and 1, they are equally likely. That is, with probability 1/2, the first agent believes that the state is 0, and with probability 1/2, the first agent believes that theta is equal to 1. And therefore, his decision will be based solely on the private signal, right? Because first, he doesn't observe any previous actions, right? Because there are no previous agent in the queue. And second, he still observes his own signal. And as we know, when you receive signal, let's say equal to 1, your beliefs are shifted in favor of state 1, right? Because it suggests that the state is 1. And if it was around 1/2, that is, if it was like your prior was exactly 1/2, if you shift slightly in favor of theta is equal to 1, then actually theta is equal to 1 is more probable for you rather than theta equal to 0. And therefore, once you receive signal equal to 1, right, without even calculating the actual probability, like which you assign now to state theta equal to 1, we can surely say that you'll choose action which will be exactly 1, right? Because you just believe that state theta equal to 1 is more likely than state theta equal to 0. And absolutely the same with signal when you receive signal equal to 0, right? When you receive signal equal to 0, you believe that it's more likely that theta is equal to 0 rather than theta equal to 1, and therefore you choose action 0, right? Therefore, all in all, we can summarize that the action of the first individual just coincides with his private signal, right? Because when private signal is 1, you make action 1. When private signal is 0, you make action 0. And therefore, what we can write is that action of the first individual, which is x, as a function of the first signal, because there are no other arguments which affect your decisions, right? You do not observe any previous choice. And based on this signal, your action is just exactly coincides with your signal, right? That is, x1 of 0 is 0 and x1 of 1 is 1. So that was the first period. Then the second period, and after the second period, this will be just, arbitrary period. So we've done 1/3 of this problem. So in the second period, it's slightly more complicated, but just slightly. Again, what you just do, you just see what you can observe and you just calculate the optimal decision. That's it. So in the second period, now things get slightly more interesting, because now on top of private signal, which is S2, right? What the second agent observes is the action of the first individual. Right? But the thing is, in equilibrium, right? When you're rational, when you observe the action of the first individual, you understand, right, that the action of the first individual coincided with the signal of the first individual, right? And therefore, once you observe the action of the first individual, you can decode the first individual's actual signal, right? That is, when the second individual observes choice equal to 1 in the first period, he understands that it had to be because private signal of the first individual was 1. And he observes, and if he observes the action of the first individual being equal to 0, then he understands that the signal of the first individual was 0, right? And therefore, we can say that actually the second individual just observes two signals, basically, right? He observes his own signal as 2, and he also observes the signal of the first individual because it just coincides with the action of the first individual. And then, based on this observation, we can summarize the action of the second individual. So suppose now the second individual, without loss of generality, let us suppose that the second individual observed action equal to 1 from the first individual. The case when x1 was equal to 0 is absolutely analogous, so I just decided not to write it explicitly here. So without loss, let us assume that the action of the first individual was 1, and therefore the signal of the first individual was 1 as well. Then, if the second individual receives signal being equal to 1, then what does he have? He has two signals being equal to 1, right? So he knows that the signal of the first individual was 1, and he observes his own signal being equal to 1. And therefore, remember that each signal being equal to 1 shifts your beliefs in favor of theta being equal to 1, right? And now you started basically with 1/2, and you have two signals which supported that the state is 1. Then obviously, it's optimal for you to choose action 1, right? Because it's more likely for you that theta is equal to 1 rather than that theta is equal to 0. In this case, it's obvious. Then suppose now that actually in the second period, second individual observes private signal S2 being equal to 0. And now you become indifferent, right? Because you started with prior 1/2 before the game. And then we assume that the action of the first individual was 1, and therefore the signal of the first individual was 1. You understand it. And your own signal is 0. And clearly, when you started with 1/2 and you have like one signal 1 and one signal 0, therefore, after all that, you get back to belief of 1/2, right? Because your prior was 1/2, and now you have one realization of 0 and one realization of one of this signal. And because of that, your belief after these two signals, it gets back to 1/2. And therefore you're indifferent, right? Between what to do, which action to do. Both will just give you expected payoff of 1/2. And here we will just assume that when you are indifferent, you always choose what is suggested by your private signal, right? So it's like when you are indifferent, you just look what your private information was and do exactly what it suggests. So you value it like epsilon more than the information from previous choices. I mean, it's not absolutely without loss, because you can observe that when you're indifferent, you do anything with any probability, right? So this won't change the actual predictions of the model too much, but it will slightly complicate the actual strategy that I will write you, right? It will still feature herding behavior, but it even will feature more herding behavior, but it's like, it's just easier for me to write equilibrium strategy if we have this assumption. So let us have it, okay? And therefore, if we agree with this convention that when you're indifferent, you choose action which corresponds to your private signal, then all in all, we can summarize your behavior as follows. That is, in this case, when the action of the first individual was 1 and your signal was 1, then you do 1. And when your signal was 0, you do 0, right? You're indifferent, you value your signal slightly more, you do action 0, right? So all in all, it turns out that in this case, again, so the second individual then just behaves solely, like you can assume that the second individual behaves solely on private signal, right? Because when S2 is equal to 1, he chooses action equal to 1. And when signal 2 is equal to 0, he chooses X2 equal to 0, right? So basically the strategy is, again, it's just you do what your private signal suggests you, right? And analogously, you can write absolute is a C for the case when the action of the first individual was 0. So in all these cases, you will get that the action of the second individual is equal to the signal of the second individual. Conditional on this assumption, right? If we, for instance, say that it's vice versa, let's say you disregard your own like signal here, and vice versa, when you're indifferent, you value collective signals, then the strategy will be different here. But you will see that it won't affect us in like long term, right? How we break these ties here. So if we break these ties as it's said here, then we eventually get these strategies optimal, right? Just to make action in the second period, which corresponds to your private signal. Okay, then the third period. where we already will see like how it actually goes. So what is again important about the third agent is that, again, the third agent can now perfectly decode the signals of the first two agents, right? Solely from their actions, because for the first agent and for the second agent, their actions coincided with their private signals, right? And therefore, when this third agent observes actions of the first and the second individuals, he perfectly decodes private signals of these two, of the first and the second individual, right? And therefore, what third agent actually observes, he observes his own private signal, which is S3, and he now knows the signals of the first two individuals, which coincide with their actions, right? And let us just see what he does. So suppose the third individual receives signal equal to 1, right? So it's like suggestive signal that it's more likely that the state is 1. And then if at least one of the actions of the first two individuals was 1, then he clearly chooses action being equal to 1, right? Because there are just more realizations of ones rather than zeros in these cases, right? When you have like 1, 1 combination, 0, 1, 1, 0 combination, it's still more ones than zeros, so it's more in favor of state theta being equal to 1 rather than theta being equal to 0. Right? So in all these cases, the third individual chooses 1. But let us suppose, alternatively, that the third individual got the realization of 1 and both x1 and x2 were zeros, right? Then here we finally have something which resembles third, right? If the actions of the first two individuals were zeros, right? Then you perfectly understand that their signals were zeros as well, and your signal is 1. And you have more signals of 0 rather than you have 2 signals for 0 and 1 signal for 1. And therefore, for you, nevertheless, you observed your private signal being equal to 1. You understand that it's still more likely that the state is theta equal to 0, right? And therefore, you will choose x3 being equal to 0, right? So basically, this is the start for herding behavior, right? That is your like your private signal here doesn't influence your decision. Next, we just have 2 more cases to cover. So the next case is like, suppose you get your signal being equal to 0, and again, at least one of x1 or x2 was 0, right? Then again, you have more realizations for 0 than rather than for 1, and therefore state theta equal to 0 is more likely, and therefore you choose x3 being equal to 0, right? And final case is, suppose that third individual got signal being equal to 0, but both actions of the first 2 individuals were 1s, that is, their signals were 1s. And then again, because you have like 2 signals in favor of state 1 and 1 signal in favor of state 0, you still believe it's more likely that state is 1, and therefore your action is just, equal to 1. So here in the first and in the third case, your private signal actually matters, right? That it's, at least sometimes, right? For instance, when you had 1 realization of for 1 and 1 realization for 0 in the previous 2 agents, your private signal was decisive. That is, it clearly influenced your decision. But in the fourth case, right, your private signal absolutely didn't influence your decision, right? Moreover, for instance, suppose that x1 and x2 were indeed 2 zeros, right? And then let us take a look. there are two possibilities. You either receive signal being equal to 1 here, or you received signal being equal to 0 here. So when both x1 and x2 were zeros, when you received 1, your action was 0. When, again, x1 and x2 were both zeros, so we are in this case, and you received signal being equal to 0, so still your action was 0, right? So you can see that once you have that realization of the first two individuals in the queue were zeros, what you get as your private signal absolutely doesn't influence your decision, right? In both cases, you just choose x3 being equal to 0, right? And what is even more important here, right? Okay, let me explain it in this slide. What is even more important now, right? So suppose the realization for the first two individuals was 0, right? And then we understand that no matter what your private signal is, third individual will choose x3 being equal to 0 as well. Then consider the fourth individual. Fourth individual still understands that if x1 and x2 were zeros, therefore the signals of the first two individuals were 0. So in terms of inference, he thinks the same as the third individual. But he also rationally understands that the third individual, right, in all these cases, like no matter what his private signal was, he always would choose 0. That is, when he observes the choice of the third individual being equal to 0, from this choice, he doesn't infer anything, right? Because anything about the private signal of the third individual, because in case it was 1, the choice would be 0. In case it was 0, it would be 0 still. So what the fourth individual infers is absolutely the same information as the third individual, right? So he knows the signals of the first and the second individuals for sure, but he has no clue about the signal of the third individual because it doesn't correlate with his choice. In any case, it is 0, right? And therefore, he basically does the same as the third individual now, right? Because again, he just knows that the signal of the first individual was 0, the signal of the second individual was 0, and the signal of the third individual, he has no clue. It could be 0, it could be 1, whatever, right? Even if it was 1, right? You know, it's 1 with some probability, it's 0 with some other probability. And even if he has some, you know, his own realization of 1, then it's still more likely for him that theta being equal to 0 is more likely. So this starts kind of a cascade, right? So the third individual just observes these 0, 0 and herds with previous ones, ignoring his own information. Then the fourth individual cannot decode the information of the third individual, but can decode the information of the first two individuals, and therefore herds with them as well, and so forth and so on, right? So just two realizations which coincide between each other, because you know we have the same reasoning for the case when x1 and x2 being equal to 1. When you have just first two actions which coincided, it instantly starts a cascade, right? All further individuals will just herd and choose the same option. What is not that tragic here is that, you know, it happens just sometimes, right? You know, you do not always have the realization for the first two individuals, it coincides. Sometimes it's different. And in this case, you know, the choice of the third individual actually reveals something for the fourth individual and so on. So, you know, you do not always have herding after two steps, right? So, but sometimes you clearly have. So all in all, it turns out that the optimal strategy when you go with this like a game tree, it will turn out to be the following. So if you observe like remember what you observe as an individual, you observe actions of the previous individuals and you observe your own signal. And it turns out that if you observe, if the number of action zeros in the previous individual's actions exceeds some threshold, which is like more than 1/2, right? Remember that you're in period T, and therefore there are T minus 1 individuals behind, right? And approximately like 1/2 plus 1, right? T minus 1 divided by 2 plus. So when you have that the number of zeros exceeds 1/2 plus 1 behind you, then you instantly herd with them, right? And disregarding of your private information, you choose the same option. If it's vice versa, if the number of action 1 is like 1/2 plus 1 individuals in the previous queue, then again, you disregard your private information and just herd with previous individuals. And only when the number of zeros and 1 is kind of in between, it's around 1/2, when it's really inconclusive, when your own signal actually matters, then in this case, what you do, you just do an action which coincides with your private information, right? And this is perfectly intuitive, right? Because when you observe too many like actions of zeros, you kind of believe, right? There are too much evidence in favor of zero, right? When you observe too many actions of ones, you believe it's suggestive evidence that z is equal to 1 and you herd, right? But what we've observed here, right, with this kind of example is that this kind of herding behavior can start with really like just few draws, right? And for instance, even if, let's say, true theta is equal to 1, with some probability, two initial guys, like the first one and the second one, can get signals being equal to 0, right? According to this table, it happens with probability 1 minus p. With probability 1 minus p, you receive a wrong signal, right? And therefore, like it's 1 minus p multiplied by 1 minus p, and already with just this probability, 1 minus p squared, just after 2 periods, you start a herding on a wrong option, which lasts forever, right? And depending on b, it can be quite a substantial probability. It can be more than 1/4, right? But still, it's a quite a substantial probability, and it's just a herding after just 2 steps. You can, if you want like herding after 3 steps, it will be some other probability, which will also be substantial. All in all, it turns out that herding on a wrong option can happen with a positive probability, with some unlucky draws, like in the very beginning. That's actually kind of the point of all that, right? And the intuition here is quite simple, right? So you have that initially there was some suggestive signals in favor of one point. Let's say you had realization of 0 for the first individual and the realization of 0 for the second individual. Then the third individual, no matter what he has, it's optimal for him just to herd with the first 2 individuals, do the same action, right? Then his choice is absolutely non-informative for the 4th individual, because he understands in any case the 3rd individual would herd with the first 2 individuals. And therefore the 4th individual has absolutely the same information as a 3rd individual. So he has his own private signal, and he's certain that at least 2 realizations were in favor of 0 for the first 2 individuals. And again, therefore, he just herds with them as well, and so on, and it lasts forever, right? And that's exactly why this phenomenon is called herding, right? Or informational cascade. So this model just illustrated this phenomenon of herding. But, I'm not saying that herding occurs all the time, because our model was particularly simple and maybe not very realistic. And therefore, like, I'm not saying comparatively recently, but in like 2000, year 2000, a paper was published which studied this question like very thoroughly and in very, very general setting, which we will discuss next. And I will just cite you the actual results, like what you should have in your model, basically, that you have a herding behavior, and what you should have for not having herding behavior. Any questions regarding this simple model first? Okay, so let us now go to this general model. I have a slide with discussion here, but we already discussed a lot. But again, just to stress here, what is important about that is that herding can occur with, like, herding on a run option, on a run belief about the fundamental can occur with non-zero probability in this model, right? Herding in general, kind of, herding after 2 steps, herding after 3 steps, whatever. Here we kind of understand herding in infinite horizon. That is, we try to look what action you make after like 1,000 steps, right? And we just try to assess whether your action corresponds to the actual state. That is, you manage to learn the state at least asymptotically, or you still make an error in your choice. And it turns out that in this model, you make an error with a positive probability. This probability does not exceed 1/2, because it's still more likely for you to learn, right? Because signals are suggestive, right? So they reveal the actual information. So it's not that tragic, right? That you heard on a run option with substantial probability which exceeds 1/2, but still it can be arbitrarily close to 1/2, right? That you make a run action in infinite horizon from today, right? And like, what is even more like general point is this, is that in this setting, when you have the sequential learning, information aggregation fails, right? That is, like, imagine that not the actions, but the actual signals were observable to all the individuals in the queue. That is, you would make your decisions based not on observed actions of the previous individuals, but on their signals. Then one can easily see that asymptotically you would make a correct decision. It's just a law of large numbers or whatever, right? Because after infinitely many signals, right, it's like more likely that these signals actually would suggest the true state of the world, right? So the only reason here to blame for this failure of like aggregate learning is exactly that you observe actions, but not the signals, right? So let us go to the general model. We are just will, formulate this model and we'll tell you the answer, and this will be. So it's a paper by Smith and Sorensen, and they considered a richer setting than this toy model. And it turns out that whether you have a cascade, whether you have this herding behavior, it depends on the signals, on the informativeness. In our example, we had limited informativeness of our signals, right? Because we could have just 2 signals, 0 and 1. And according to the bias rule, right, when you had some prior, right, any signal, 0 or 1, could shift our prior belief within some bounds, right? It couldn't make it arbitrarily close to 0 or arbitrarily close to 1, right? I will explain it in the next slide a bit more. But in our example, it turned out that informativeness of these signals was bounded. And it turns out that in these cases, it's indeed true that with non-zero probability, you have herding behavior. And it turns out that when it's vice versa, you have signals of unbounded clearness, let's say, which are like almost perfectly clear. Then it turns out that asymptotically, agents will learn the true state correctly. So it turns out that the actual determinant of whether you have herding behavior or not is exactly the clearness of signals. And the intuition here is as follows. In our example, just let's say the signal of the third individual in our example, it couldn't overturn two signals of the first two individuals, right? Because all signals were the same, and when you have two signals in favor of, let's say, state 0, when you have signal in favor of state 1, it's still not enough to overturn evidence in favor of state 0, right? But if we assume that we have richer set of signals, right, with arbitrary clearness, then with some probability, if the true state is actually 1 in this example, right, with two signals being equal to 0 for the first two individuals, when you have a very strong signal in favor of state 1, you will still choose action 1, right? And then the next individual in the fourth period will understand rationally, right, that if it turned out that the third individual, nevertheless having first two zeros, decided to make action 1, it had to be that it was because of very strong signal in favor of 1, right? And therefore this cascade would be overturned, right? But in our example, we had that one signal in favor of 1 would never be two signals of 0, right? But when we have a richer set of signals, when it can be that case, then it turns out that asymptotically, correct learning will occur. So the model is as follows. So again, time is discrete and infinite. And again, there is just a binary state, and both states are equally likely. That is, with probability 1/2 state is 0, and with probability 1/2 state is 1. And again, you have a queue of agents that arrive sequentially, make actions, again, observing their own private signal and the choices made by the previous individuals. And here, we assume that the action set is a bit richer. That is, you have, in any period of time, you have k actions to make, not just 2, right? It's not that it's action 0, action 1, like it was in our example, but a richer set of actions. And they are as follows. So, for instance, assume action 1. It can be represented with this line. That is, when state is equal to 0, it gives this payoff, and when state is 1, it gives this payoff, right? Then action 2, in state 0, it gives this payoff, and in state 1, it gives this payoff. Action 3, it gives this payoff in state 0, and it gives this payoff in state 5. And another action 4 in state 0, it gives this payoff, and in state 1, it gives this payoff, right? So what is important is that for some beliefs, and here you can say that this on a horizontal line is just belief, like about the probability that theta is equal to 1, right? So when you, for instance, believe that it's very likely that theta is equal to 0, then it's myopically optimal for you to make action A1, right? Because it is superior to any action within this region. But when your belief is kind of like slightly higher, then it turns out that it's myopically optimal for you to make action A2, right? Because you are uncertain. Then it's optimal for you to make A3, and here in this region, it's optimal for you to make A4, right? So you have some set of actions, and any actions is sometimes optimal to make myopically. Remember that all the agents in our model are myopic, right? Once they make this decision, they exit the market, right? So they are not long-lived, like in experimentation, for instance. So here, you exactly do myopically optimal decisions. And what is important, we assume that you do not have a dominated action here. That is, for some beliefs, like for some probabilities that the state is equal to 1, any action can be optimal. So for here, it's illustrated, example with 4 actions is illustrated. That is, all actions are sometimes superior to all other actions. So in these regions, A1 is optimal, in this region, A2 is optimal, in this region, A3 is optimal, and in this region, A4 is optimal. Right. So it's just, it's not that important for the results, but, we want to have a richer setting here, right, to make it quite general in terms of predictions. And again, how you make your decision is the same. So you observe the actions of the previous individuals. Now it's kind of a richer sequence, right? It's not just a sequence of zeros and ones. It's indeed a sequence of some A's, right? For any action, you can have like K A's here and so on, right? So histories here are potentially very rich. And on top of it, you observe your private signal. So how private signal is modeled here? We just assume that you have some distribution of signals conditional on each state. That is, when you have that theta is equal to 0, right? You have some particular distribution of signals that you receive, right? With some support. I'm not even saying like on which support you have these signals. For instance, you can assume that it's like normally distributed signal with mean theta equal to 0, right? And when theta is equal to 1, it's again a normally distributed signal with mean equal to 1. And let's say in both these cases, the variance is the same, for instance. But even that is not assumed. That is, you just have some distribution of signals when theta is equal to 0, and you have some alternative distribution of signals when theta is equal to 1. Just some arbitrary distributions in both these cases. So here, so how the inference procedure takes place. So assume we are in a place of time t agent, and here infers some information about the true state, about theta, from the actions of his predecessors, right? So here, this inference is particularly complicated because all these actions, these are some A's, right? A3, A5, whatever, AK, like lots of them, right? So here it should be T, so it's not K, it's T. So there are lots of possible histories, and therefore to tractably write what belief it gives you about theta is it's not possible. We therefore just summarize that the resulting, like, let's say, public belief, right, based on public information, we just call it PT. For instance, in an example with hotel, when you choose a hotel, right, when you just Google a hotel, these access, right, these are just reviews of previous customers, right? This is a public information from previous experiences, and therefore it forms public belief, right, PT. So this PT is exactly this rating, let's say, right, that you observe, like 4.3 out of 5 stars. And then let's say you experience this hotel and you receive your private experience, right? And in our language, it's exactly your private signal ST. Oh, no, that's it. No, I'm wrong here. Sorry. I'm going slightly in a different direction. No, ST here is exactly just your personal view about this hotel before you actually experience. So it can be, like friend's suggestion, your own just, impression after you looked at in Booking, for instance, or whatever. So it's just it's your private information, right? So it's kind of something which is not publicly observed about this. And together with this public belief, your private signals, they together form your private belief, right? That is your private views about this hotel. That is your private views, they are based on public information from previous customers and your own private signal, right? And given this, BT, like your private belief, you choose action which is myopically optimal. That is, you calculate PT, it's somewhere here, you receive your own signal, it shifts public belief somewhere, right, on this axis. And then you just look which action is superior for this private belief, and you just make this action. So it's like that for you. So let me also finally write you an alternative form for the bias rule. So how it goes here. So PT is a public belief, which is based on previous experiences of others. Then you have this ST, your private signal, and then this forms private belief BT. Let us write it in a bias rule. Let's say PT is your prior, right, which is based on public information. Then you observe signal ST, which makes you recalculate probability of theta being equal to 1 to BT. According to the bias rule, it's like that. You start with prior PT, that is probability that theta is equal to 1, right? You enter it here, and here is the probability that theta is equal to 0. And here is exactly the probability to observe ST. You observed now ST, right? So here is a probability to observe ST conditional on state being equal to 1. And here is a probability that state is equal to 1. So here it's the same probability. So here it's not actually probability, it's density, right? But it's like a straightforward generalization for the bias when you don't have like probabilities, but density. Here is the same density, and here is like density of probability to observe exactly ST conditional on the state being equal to 0, right? So that's exactly how you calculate your private belief, right? You start with public belief, then you observe ST, and here you just substitute like how likely it is to observe ST in state 1, and here is like how likely to observe ST in state theta being equal to 0. This bias rule can be alternatively rewritten in the following form. Because this is BT, 1 minus BT, right, is 1 minus this fraction. And when we take 1 minus this fraction, we'll have this term in the denominator, and denominator will stay the same, right? And therefore, once we divide BT by 1 minus BT, we'll have a simple expression for that, right? Alternatively, it turns out that the bias rule can be written in the following form. That is what is called when we have belief, right? BT or PT, this is just belief. When we write like belief divided by 1 minus belief, it's called odds ratio. Odds ratio is something that you have in betting, right, on horses or whatever. It's like 5 to 13 or whatever. It's not exactly what is called odds ratio. It's like chances against this event, whatever. And therefore, the bias rule can be written in the following form. That is, your posterior odds ratio is your prior odds ratio multiplied by this term, right? And this term is called likelihood ratio. It's like how likely it is to observe ST in state 1 relative to the probability to observe ST in state being equal to 0. For instance, when we go back to our very initial examples for the course, right? When we had that ST occurs, let's say, only in state theta equal to 1, right? Then this would be 1 and this would be 0, so it will be infinity, right? And therefore, irrespective of the prior PT, BT would jump to 1, right? 1 because it's 1 to 0. So it will be exactly infinity. And when it's like the same probability to have ST in either state, then it will just reduce to 1, and therefore would cancel out, and you instantly observe that the posterior BT will be equal to the prior BT, right? So you can see clearly here, right, that if you have that ST is more likely to occur in state theta being equal to 1 rather than in state theta equal to 0, then your posterior goes higher, right, than the prior. When it's vice versa, then it's vice versa, right? Then BT is smaller. Sometimes this form is more convenient. In research, actually, it's very widely used because, you know, it's simpler. What the authors also assume about the primitives about the primitives in this paper is that they assume that this ratio, this likelihood ratio, is strictly increasing, right? That is, it means that this F is such that this ratio is strictly increasing. And this means that when you have higher realizations of S, right, this fraction is higher, right? When you have higher realization, this is higher, and therefore your posterior is higher, right? That is, the higher is ST, the more it's suggestive that, you know, that theta is equal to 1. It's kind of a standard, it's a very standard assumption. It's called monotone likelihood ratio property. It's kind of a minimal assumption on these distributions. So, and that's actually it about the model. So next we'll just state the result, and that will be. So let me now illustrate you what is like bounded beliefs and unbounded beliefs. So suppose you had some prior, right, which is based on public information. In our toy model example, this public belief was exactly the belief, like, for instance, we take the third individual, right? Then his public belief was solely based on the realization of the first two signals, right? This is exactly the public signal. And then he observed his own realization, and this is exactly this term, right? So how you form your own belief is like it's a public component, and here is exactly your private signal component. And we say that, okay, first let me stress that because we assume that this likelihood ratio is monotone in S, that is monotonely increasing in S, then, you know, it has to be, you know, it has to have its upper and lower bound in general sense. It can be minus infinity and plus infinity, whatever, right? But there are some bounds, right? And there can be two cases generally. Like we will call beliefs bounded if the lower bound and the upper bound for this ratio, these are finite numbers. Clearly, I mean, like you can't have minus infinity, so, but you clearly can't have 0, right? So because densities are always positive, at least not negative, right? And therefore you can't have negative numbers here, but you clearly can have something arbitrarily close to 0. And vice versa, you can have the ratio of densities being arbitrarily close to plus infinity. Right? And we will see that this likelihood ratio, that beliefs are bounded if there exists f lower bar and f upper bar, such that this ratio is always within their bounds. That is, it's always above f lower bar and it's always below f upper bar, and these bounds are finite, right? That is, this ratio is within some bounds, and these bounds are finite. In this case, we will call the model as the model with bounded beliefs. This is exactly what it was in our toy model, right? Because whenever you had some public belief, which was based on the experiences of previous individuals, when you calculate this ratio, it would be P divided by 1 minus P, something like that. P, remember, it was some probability, exogenous a given probability from the table, right? So, and P is just some number, and therefore clearly P divided by 1 minus P, or vice versa, 1 minus P divided by P, you know, it's clearly within some bounds, right? In any case. And therefore our model was exactly with bounded belief. It means that like when you start with some like prior, you cannot have arbitrarily far jumps from your prior, right? That is, when you have that this ratio is bounded, it's within some bounds, then when you start with some prior, you cannot jump in terms of your private belief too far from it, right? You have that your jumps will be only within some bounds, right? Because when you substitute f upper bar here, right, then you can recalculate the highest possible jump in terms of BT from the current PT. And when you substitute f lower bar here, you can calculate like the highest jump to the left, right? From your PT to BT. Therefore, when you have bounded beliefs for a fixed prior PT, you cannot jump too far from your current, right? You are always within some bounds in terms of your jump from your current prior. And vice versa, we call the model with unbounded beliefs if the lower bar for this fraction is 0 and so the upper bar is plus infinity. That is, it means that there do exist signals which are arbitrarily precise, right? Because when you have a signal for which this ratio is almost at 0, right? Then this whole term in the right-hand side is almost 0, and therefore BT is almost 0, right? And when we have that this ratio is plus infinity or very, very large, then irrespective of PT, this right-hand side is arbitrarily large, right? Because this is just a constant. And therefore BT is arbitrarily close to 1, right? For it to be arbitrarily large. That it means basically that you have signals which are arbitrarily clear in some sense, right? And it turns out that these two scenarios, they are very distinct, right? So in this case, when you have bounded beliefs, and in this case, when you have unbounded beliefs. And it turns out that the theorem is as following. So when you have bounded beliefs, it turns out that herding on any, like, remember that there are lots of actions here, right? Not just 2 actions. There are k actions here. And it turns out that according to this theorem, we're herding on any of these actions except the least optimal. That is, the least optimal is the following. That is, when your true state theta is equal to 1, the least optimal is A1, right? And when your true state is zero, then the least optimal here in this example is A4, right? And it turns out that herding on any action except the least optimal for this state can occur with positive probability if beliefs are bounded. If you have that, this likelihood ratio is bounded, basically. And vice versa, if you have unbounded beliefs, that is when your signals are such that this likelihood ratio is from 0 to plus infinity, right? Then asymptotically, the agents will learn the true state correctly. That is, they will make action A4 when true state is 1 in this example, and they will make action A1 when the state is 0. So you see there are just, very different patterns of behavior in these two cases, right? And that's it, more or less. Next, I will just describe you briefly the intuition. This will be the last slide. But I've already verified the intuition before, but once again, why it's important? Because when you have bounded beliefs, right? When you're somewhere in between, and let's say you do some intermediate action, right? Then in terms, like you make some action, and then, any private signal can shift you from, current public belief only by not too much, right? It cannot make you jump, arbitrarily close to the correct action. And therefore, you sometimes can be doomed to travel around, intermediate values, and that's it, right? And be trapped there. But when you have like arbitrarily strong signals in favor of some state, then even when sometimes you can still travel there, sometimes these very strong signals will occur, right? And they will make you jump arbitrarily close to the true state, and since then, on average, you won't leave it, right? So intuition is more or less like that. Why that is at all important. And that's almost it for today. So what we did, we started with a very basic model, which illustrated the concept of herding, that is how it can occur, how we can observe that it's rational for people just to imitate behavior of others without actually relying on their own signal. And then we analyzed a more general model where we actually see from what this behavior originates, right? That it turns out that the main source for the herding behavior is exactly as a structure of signals. That is, when you have bounded in terms of the informativeness signals, then it turns out that herding on wrong options can occur with positive probability. We are not saying that it's like very large probability or like just some positive probability. It's still kind of, it's still a possibility that in infinite horizon from today, you still make a wrong choice, right? Which is no matter with what probability, it's still not good, right? But it turns out that when you have signals which are arbitrarily precise and arbitrarily strongly suggestive about the true state of the world, then herding is kind of an artifact of like very limited time horizons, but in long term, people will still learn the true state correctly and be. So that's like the main conclusion. Any questions regarding all that? Then that's it. And on Saturday, hope we'll have a midterm. Hope we will be fine with all the technical details and all the technical obstacles that we have now, but I will inform you of something. Okay, then that's it. And bye and see you on Saturday.
Excuse me, I have a question. Could you please clarify once more what is the set of the probable actions in the second model is? What does K mean in the
So
upper index?
yeah, I mean, like these are some actions, and it's like when you just decide on these actions, right? You do not know what the true state is. That is, you have some, let's say, some action A1, and if the true state is 0, it will bring you exactly this value. There is some numerical value here, right, on this axis. And when the state is 1, it will give you exactly this. That is, suppose you decided to choose A1 as an action now, and then, there is some true underlying state, and it will give you either this payoff or this payoff. But this payoff is not observable for further generations, right? They just observe that you made the choice of action 1. How much did you get from it? They don't know, right? And therefore, when you have that, when state is 0, you get that much, and when state is 1, you get that much. When you have some intermediate belief, right, here it's corresponds to certainty that the state is 0, that is belief being equal to 0, and here it's belief equal to 1. When it's some kind of intermediate, it gives you on average, from your perspective, exactly what is on the line right here. So here it's exactly the expected payoff from action 1, conditional on any type of private belief that you can. Then for action 2 is the same. So when state is 0, it gives you that much. When state is 1, it gives you that much. Suppose you decided to make action A2, and then, conditional on the true state, you receive either this or this, right? And according to, if you have some intermediate belief, in your view, you get exactly what is on this line, something like that. More or less
Okay,
clear?
thank you very much. Yeah, it's clear now. Thank you.
Okay, then that's it.
Thank you. Goodbye.
Mm-hmm.